Okay, students, let's take some time now to study the ionization of weak acids. And as we discussed before, some acids do not ionize completely when you dissolve them in water. Rather, they establish an equilibrium. And if we consider the ionization of a weak acid, we're going to use the generic expression here, HA, to represent the weak acid. Again, remember we represent it with a double arrow indicating this is reversible. But because this will arrive at an equilibrium state, we can consider an equilibrium constant. We're going to call this equilibrium constant Ka, the acid ionization constant, and it will describe the equilibrium that forms when an acid reacts with water. The expression for Ka, again, would be this. It would be the product of the ionized acid times the hydronium concentration divided by the concentration of the unionized acid. Remember that because water is the solvent, we don't include it in the equilibrium constant expression of Ka. Now, I'm going to put a statement here and I want you to think about it and pause the video if you need to make sure that you understand why I'm going to say this. The larger the Ka value, the stronger the acid. Okay, pause the video if you need to. The reason I'm saying this is because you have to remember the Ka is ultimately a ratio, right? It's a ratio of products over reactants. If Ka increases, that means that the ratio of products to reactants is increasing. There's more product. In other words, there is more of the ionized forms of the acid. So that means that this is a stronger acid. Of course, stronger is kind of relative. We probably would say the less weak it is. As we go along, you'll find this table very useful. And this is from one of our textbooks, but you don't have to memorize it. All I want you to do is make sure that you have either a copy of it with you or you have it bookmarked in your text. You know where to reach it, but mostly you know how to use it. So how do we use it? Let me borrow here my highlighter and let's look at nitrous acid over here. Notice that they give you first of all the name of the acid, then they give you the formula, and notice that they've highlighted in red what we call the acidic hydrogen. In other words, the hydrogen that is going to ionize out. Notice that when you look at formic acid or benzoic acid, notice that there's other hydrogens in the formula. However, there's only one, and later on we'll see maybe 2 or 3 that will actually ionize. I already jumped ahead, but as you can see over here on the next column, they give you the formula of the acid, and you can see where that hydrogen is. That's acidic. So this would classify as an oxy acid or oxo acid. Then they give you the ionization reaction. Remember that for the ionization of weak acids, you're going to identify them because there's a double arrow in there. And here is the value of Ka. And you'll notice that this is arranged in order of from stronger to weaker acids. In other words, it increases as you go up here on this chart. There's a last column here called pKa, but we're going to use that in our next unit. Okay, so that's how those things work. Now let me see if I can erase these things before we go to the next slide. Okay, here we go. So let's go ahead and see how we use these values of Ka to compare the relative strengths of different weak acids. So if we examine the equilibrium constants for the acids, quote-unquote, reaction with water, essentially their ionization in water, that equilibrium constant that we're calling Ka is going to help us determine which acid is stronger. So let's consider this one here. This is hydrocyanic acid. And let's consider this other one here. This is acetic acid, the component of vinegar. If we look at the table, we'll see the expression of Ka. Again, remember, products over reactant. So for HCN, the value of Ka is 4.9. times 10 to the negative 10. For acidic acid, again, products over reactant, the Ka value is 1.8 times 10 to the negative 5. So question number 1, and again, please pause the video and think about this. Which of these acids is weaker? Okay, the one that has the lower value of, or the smaller value of Ka. Sometimes with expressions in scientific notation with the exponents being negative, sometimes students get confused. Remember, the more negative an exponent is, the smaller it makes that value, right? Because it means the more spaces you've had to move the decimal period to the left of the number. So effectively, HCN is the weaker acid because it has the lower value of Ka. Next question. Which of the two forms the greater concentration of hydronium ions when equal concentrations of acids are added to water? Okay, let's assume you have, let's say, 0.1 molar of each in different containers. Which one do you expect to have the greater concentration of hydronium ions? Pause the video and think about it and come back. Right, so the way to think about this is hydronium is on the products side of the equilibrium. So it means that to have a greater concentration of hydronium means that the equilibrium has to be in a position that's a little farther to the products side. It favors the products more, and that means it is an equilibrium that has a greater value of Ka, and the one with the greater value of Ka here is the acidic acid, the CH3CO2H. Very good. I'm going to let you practice now a little bit more of this. So which of these two solutions has the greater concentration of hydronium ions? Here we have 0.1 molar HOCl, that's called hypochlorous acid, and 0.10 molar of HCN, hydrocyanic acid. By the way, you don't need to know the names of these acids at this point. I'm not going to force you to do that. Remember, you do have a assignment to memorize the names and formulas of the Magnificent Seven, right? The 7 strong acids that we use in the lab commonly. Okay, so here are the Ka values of each. I'm going to give you time to pause the video and think about this question and see which one has the greater concentration of hydronium ions. Okay, so remember, the more negative the exponent on the 10, the smaller the value. So in this case, since the concentrations of each acid are the same, the only thing that's going to determine the concentration of hydronium ions, which is on the products side of the equilibrium, is going to be the value of Ka. And we can see here that the stronger acid will dissociate, will ionize more, and therefore put more hydronium ions in solution. In this case, since HCOl has the higher value or greater value of Ka, it will therefore have the greater concentration of hydronium ions in solution. Now remember also that when you have an equilibrium, you have a conjugate pair. So in the equilibrium expression in the reversible ionization, the acid is paired with its conjugate base on the product side. So if you were coming in the reverse direction of the ionization of that base, you could establish, which one is weaker, which one's stronger. So here's the rule of thumb we're going to use. The stronger the acid, the weaker the conjugate base. So here's a table that shows you on the left a selection of some of the weaker acids, not all of them. And again, like I said, to say weakest or strongest is really relative because none of these are strong acids anyway. You can tell by the Ka values. So notice, for example, that nitrous acid, which was the one that we studied earlier, nitrous acid is here, has a 5.6 times 10 to the negative 4 Ka. So in this set is one of the stronger acids. If you compare it with, say, HCN, you can see that HCN has a very small value of Ka. And so HNO2, nitrous acid, is a stronger acid than HCN, hydrocyanic acid. But if you take their conjugates, in other words, their conjugate base, and you take that and ionize it in water, okay, it's not, this is not the, I'm not talking about the reverse of the ionization of the acid. I'm talking about putting this substance now in water to act as a base. You can see where the cyanide ion is a lot stronger than the NO2 negative, or the nitrite ion as a base. So again, the stronger the acid, the weaker the conjugate base. And we'll talk more about these in numbers with math in our next section, in our next unit. I'm sorry, in our next section of this unit. Another thing that we have alluded to and didn't discuss is acids that have more than one acidic hydrogen and can thus donate more than one hydrogen ion. These are called polyprotic acids, and we see 3 examples of them on the right. The top one is called phosphoric acid, followed by carbonic acid, followed by sulfuric acid. So, in a reaction with a base, these acids will donate more than one hydrogen ion. Now, when you dissolve them in water, what happens is the acid donates the hydrogen one ion at a time. In other words, the ionization occurs in a stepwise manner. And therefore, excuse me, the Ka values for these are different. So we label them to indicate which step in the overall process we're alluding to. So we have Ka1, Ka2, Ka3, and so forth. If you look at this table here, again, of some commonly known polyprotic acids, and again, you don't have to memorize this, you just need to know how to use these numbers. You can see over here, for example, citric acid, as you can see, has 3 ionization constant because it has 3 acidic hydrogens, right? And one thing you can probably make note of is that, well, actually, let me ask you, what do you notice about these successive values of Ka, Ka1, Ka2, Ka3? Exactly. Notice how in all of them, Ka1 has a larger value than Ka2, which in turn has a greater value than Ka3. So in other words, each successive ionization is weaker and weaker. It's less likely. One special case perhaps here is sulfuric acid. You can see where it is diprotic. In other words, it has 2 acidic hydrogens. Notice that the first step is actually a strong ionization. In other words, sulfuric acid is a strong acid, but that is with respect to the first acidic hydrogen. The second acidic hydrogen, on the other hand, as you can see here, is a weaker ionization. So those are some observations that we can make of these. Okay, so let's do a little practice here. Oxalic acid occurs in plants and foods such as parsley, rhubarb, almonds, and green beans. Here are the Ka values for the 2 ionization steps of this acid. The top one, the first ionization, Ka1, is 5.6 times 10 to the negative 2. Ka2 is 1.5 times 10 to the negative 4. Now the question is, besides water, which ion or molecule has the highest concentration in solution when oxalic acid is added to water? Pause the video and think about this question and see if you can come up with an answer, and then we'll come back. Okay, let's see what our thought process should be. Notice, the first ionization constant of this acid is a small number. It's less than 1. In other words, this is a weak acid. Because of that, you expect that at the first ionization step, most of the acid remains unionized. The second ionization is even weaker. So what we conclude therefore is that because that Ka1 value shows that it is a weak acid and ionizes only to a small extent, that means that most of the oxalic acid is present in water as H2C2O4. In other words, the non-ionized form. Okay, we have taken a brief survey of the equilibria that are involved in weak acids and a little bit of polyprotic acids. Now it's time to get some quantitative measures and also discuss how did we arrive at those values of Ka. So we'll go on to the next section.